So I think we can start slowly. All right. Welcome to our webinar with the topic low frequency MEMS ultrasound transducers. For those of you who haven't seen our past webinar series, I shortly want to introduce myself. I'm Stefan Tietze and I'm part of the business development team at the Fraunhofer IPMS and will be the moderator for this webinar today. And at IPMS, we are focusing in our research on photonic microsystems, which includes micromirrors, micromirror arrays, and actuators, as well as wireless microsystems. Especially our new design approach of the nanoscopic electrostatic drive, shortly called the NED, is one of our latest research topics. You already have heard of this approach in one of our last webinars about the power of the micropump by Christina Rufford. And besides this application as micropump or microvalve, the NED has also big opportunities in the field of low frequency ultrasound. And this topic will get our main focus for today. And so I'm glad to introduce the group manager and deputy manager of the business unit monolithic integrated actuator and sensor systems, Dr. Bert Kaiser. Bert studied microtechnology at the Hochschule Mittweida and did his master degree in microsystems and microelectronic at the Technical University in Chemnitz. Afterwards, he did his PhD with the topic simulation and characterization of a novel micromechanical electrostatic actuator at the Technical University Cottbus, in cooperation with the Fraunhofer IPMS. Now, Bert and his team are focusing on the research field of silicium-based bulk microsystems. In total, the webinar will approximately run for 20 to 30 minutes, and afterwards we will answer the questions you can ask during the webinar by using the question function. So feel free to ask during the webinar. Additional, the slides of the presentation will send out to all of you. And in total, I want to take it short and have the pleasure to hand over the voice to Bert Kaiser. Welcome, Bert.
Thank you very much, Stefan. Thank you for the introduction. Thank you for listening. Thank you for joining. So my name is Bert Kaiser, as you already know. Thank you for the brief description of my vita. So you already know who I am, and I want to begin with where I am. So I'm here in my office in Dresden, so at the headquarters of Fraunhofer IPMS, but we do have two more locations which are in Cottbus and in Erfurt, with a total of 450 colleagues working all together with us and an annual budget of roughly 43 million euros in 2018. What is important to know is that we do have our own MEMS fabrication facilities here in Dresden. This is just next to my office building here. You see it in the picture, which is a 1,500 square meter clean room of ISO 4, so class 10, and is able to process 200 millimeter wafers, so 8-inch wafers. Besides simulation and several other R&D topics which we do for our customers, we are therefore also able to start a pilot fabrication. So several thousand devices if necessary. We are also ISO certified, which is a lot of work every year, of course. So let's start with the topic. Stefan already mentioned low frequency MEMS ultrasound transducers. And that's what I want to outline. So what's the frame? What's the picture I want to draw today? So let's start with a few facts about ultrasound. And then we directly step into the technical insight of our technology, of our low frequency MEMS ultrasound transducer technology. And we will have a brief overview of example application, which will be gesture recognition. So let's start. Why ultrasound? What are the benefits? So we have a non-radiative, non-destructive technology, which is from 1D to 4D possible. It is not sensitive to light scattering or light shattering. And we already know it from everyday life, or most of us will know it from everyday life. So the most prominent examples will be like park assisting or medical imaging. And let me go through the graph here on the right side, where we see these different application fields like medical ultrasound here, with the very famous baby picture, and the fingerprint sensing, gaze recognition, and the park assist. When we see this graph, we have here 3 different technologies, which is PMUT, CMUT, and bulk technology. They are different for the art of making them or for the materials upon which they are based. So in the field of gaze recognition, which is a bit significant in this picture, we see this is something like an emerging market. So in 2007, according to this graph, there was nothing. And in 2023, there will be everything, so solely based on PMUT devices. So why PMUT? Why not CMUT? Why not electrostatic? That brings me to my next slide, which shall give a short overview of the frequency range. So what are we talking about? So if you see these frequency range from several hertz to several 10 megahertz, the ultrasound range is normally beginning with, let's say, around 20 kilohertz. And we have at IPMS the technology which we call NEDMUT. Before I come to the details, to the technical insights, I want to talk about the rest of this graph here. So for the lower frequency range, which is what humans normally can hear, the audio range, we have the NED audio transducers, and for the higher frequency range, we have the CMUT devices also at IPMS. So we can cover the full frequency range. Apart that, in the Fraunhofer Society, there are also other technologies like the PMUTs for the higher frequency range or the piezo MEMS in the lower frequency range, or even the bulk piezoceramics in the in the ultrasound range. What I now want to concentrate on is the low frequency range, where we have distance measurement or gaze recognition, and where we at IPMS have the NEDMUT technology. So let's step into the technical details. So NEDMUT, what is NEDMUT standing for? This is what Stefan already described as our new nano e-drive technology. And it's like the CMUT, it's the micro-machined ultrasonic transducers. On the left side, you see a big picture of our demo device, which is a NEDMUT demo chip. It's an all-silicon device, so it's a wafer stack. You can see it on the left corner, or you can get an idea of that. So it's 2 wafers bonded together, and it has the all electrostatic drive within, which is the nano e-drive. That brings me to my next slide, which describes the 2 basic principles of our NEDMUT devices, which is the nano e-drive and bending electrostatic cantilever in this case. And the second aspect or basic principle is the volume utilization. So instead of having an surface micromachining or an, like, let's say, active surface area, we do transform the active components into the volume of the chip. And the combination of both, so the powerful NED actuators and the volume utilization, allows us to create low frequency and really powerful devices compared to about the footprint, let's say the footprint. So what's behind both basic principles that I want to show you on the next 2 slides. So the nano e-drive itself, that's the drive, that's the motor, the source of deflection within the device. And it's on the right picture, it's depicted for you with a standard configuration, so 2 electrodes, of course, with a special geometry. So we have the lower electrode in this area, the upper electrode, which is highlighted in green here, and of course the electrostatic gap, while both electrodes, of course, are kept in a small distance via isolation spacers. Of course, they shall not be electrically conductive. Over this gap, and that's now a benefit of the MEMS technology, this gap could be really small. We have the electrostatic forces, the Coulomb forces, and due to this very small gap, we have comparatively high forces with low voltage. And that leads to a very powerful actuation. And of course, from the physics, we can turn around the transduction mechanism. We can also have a powerful sensing. Having that activated, that comes to this small animation I want to show you. So we have this bending of the top electrode, which creates something like a surface stress in the actuator and makes the cantilever bending. I guess it's not hard to understand that, of course, we can have several different shapes of these electrodes and therefore will influence the bending capabilities or sensing capabilities. And of course, we not have only the possibility to deflect out of plane, but also to deflect in plane. Having this technology allows us to leverage the MEMS benefits, which is of course efficiency, precision, reliability, and with our all electrostatic principle, we have the so we do not rely on special materials or any external coils or something. So we are compatible to most of the clean room facilities, and we do not have some special materials which may be restricted in use, especially in the EU. Miniaturization, of course, is like an inherent benefit of the MEMS. And that's what leads me to my next slide. That's the second basic principle, that's the volume utilization. What does that mean? And that I want to start with the picture on the lower right here. That shows on the layer stack, you see these 3 layers with a small distance, which is some gluing, as I want to say. And we have the actuators, which are now a clamped version here in the middle layer as the active part, always arranged in pairs. And as they deflect, of course, they track or displace some air. And this air is then pushed out through openings in the bottom wafer or on the cover wafer. To make this even more clear, I put in here this cross-sectional view. So again, we have these 3 layers, where the middle one is the active one with the actuators moving in one time slot towards each other, and in the other time slot apart from each other, and therefore creating pressure waves, which is sound. And in the right frequency range, we will then create ultrasound. With that approach, we utilize the volume and therefore we in principle have the surface free for other integration aspects. In this picture, you see the holes in the top wafer or bottom wafer, but of course you may easily imagine that these openings could easily be in the front side. So we have something like a side firing device. And then it's really just a plain surface. But of course, this plain surface is necessary to close these air chambers and not to have an acoustic shortcut on the front and the back side of the actuators. We do have a small channel depicted in that picture, which ensures movability of the actuators, but will not become acoustically active since to the very small dimensions. Let me highlight these possibilities on the surface. So we, of course, first is to implement some electronics or use it for the packaging or make some passive structures to influence the acoustic field or something, or even stack if you want really powerful devices and you don't want to higher the footprint, but you do have some space in the thickness, of course you can then stack the devices. With this approach, as described in the slide, we have also an inherently robust design, and what is meant here is that the electrode gap, which is within the electrostatic drive, as I showed on the previous slide, it's shielded by the cover and bottom wafer, so it's within this bar here, and every particle or something is prevented from getting into this gap because of the concept. What else is to be said about the design is on the next slide. So we have the fabrication. How do we create this design in the clean room? So we start with these bonded silicon on insulator wafer. So it's actually two wafers glued together via silicon oxide. And we mostly rely on deep silicon etch, where we do first a lithography step on the surface and then just extrude this very precisely defined geometry into the depth of the device. Additionally, we have to create these spacers, which is here this orange part within the actuator. And then we create the openings in the backside, where the air will later let in and out of the device. And of course, in the end, we will glue the cover wafer to the stack. Of course, this is a very short explanation of the fabrication process, but this is the main step. These are the main steps. And of course, we rely on a highly doped silicon wafer to ensure the conductivity for the electrostatic principle. What comes out if we fabricate these NEDMUT devices? That's shown here. So we have on the lower right side again this picture of an, let's say, uncovered device, so without the cover wafer. This is a top view of the device layer, where we have, you see, these 9 groups of NED structures. The outer 4 are the receiving structures, 2 different versions, which are optimized for receiving, so for sensing an ultrasound field, and the middle ones are optimized for emitting an ultrasound signal. So there are 5 individually addressable transmitter structures, which is a very basic array if you want. These very first devices have a mechanical resonance of 40 kilohertz and electrical capacitance of below 350 picofarad, and they are driven by a bias voltage of 24 volts plus an alternating signal of 24 volt peak. What happens with this driving is the movement of the actuators, and I included a cross-sectional view here. You see this is from an actual specimen. This is cut, and we have this microscope picture here, so you see the inlets and outlets, if you want, in the cover and bottom wafer. And I made here a zoom picture, the very small actuators moving in the active layer of the layer stack. These actuators here in the clamped version, they have a certain thickness, length, and geometry. So the electrode shape, which is describing the performance of the actuators. And from the length, you can roughly guess which frequency range we can address with this technology. And if you use this rule of thumb here, you can easily estimate that we can go to the lower 100 kilohertz range, which is all the topic of this slide set, low frequency ultrasound transducers. So while driving, what comes out of these actuators or this demo chip? So we made several measurements, of course, and I want to show you 2 of them. So from this very first demo chip, we have just 1 transmitter active at this 40 kilohertz resonance, and we get like 100 dB at 1 centimeter in the free field distance. Of course, this is then lowered by increasing the distance. We also have the angular sound field as you want, or of course directly in front it's the highest sound field in 9 centimeter distance this time, and it's lowering to the sides. Of course, if you drive these 5 transmitters with a phase shift, then you could actively steer the sound field. This chip is what is the core of our low frequency MEMS ultrasound transducers. But of course, you need some electronics to drive it. And while in the laboratory there are a lot of huge electronics to drive this thing, we also built a small evaluation kit for application, which is based on a Raspberry microprocessor and includes a specifically designed MEMS carrier board where the actual core component, so the NEDMUT device, is glued up on, and this whole system is able to capture 30 frames per second with a range up to 30 centimeter. The MEMS device alone, so the MEMS component, is able to create or to sustain really efficient driving. But of course, it's always, for the whole system, it's always connected to the drive-in circuitry. How efficient is this? And that's what we also did. We developed a first analog control unit. So we named this ACU. It's an integrated ASIC, so an integrated circuit. And it helps to maintain the efficiency. It has a very low current drain, and it also can be battery powered by a standard 3.7 lithium-ion accu. Okay, that's the technical insight. Now let's get to the application. So I want to divide the application by field, domain, and then by frequency. For, let's say, airborne ultrasound, it's important to have another rule of thumb kept into mind in your mind, which roughly says, okay, the damping is proportional to the square of the frequency, which of course has two meanings. So increasing the frequency will limit your distance, how far you can go. But increasing the frequency, of course, helps to create really high resolution. And to give you two examples, so with our low frequency approach, we are targeting mid to far distance. So let's say 2 centimeter to 1 meter. And with high frequency, the technology which we have also in our institute, we could have, for the airborne applications, we could have really short distances, like let's say up to 4 centimeters, but really high resolution down to several micrometers. The high frequency would be used for surface inspection, spectroscopy, or of course like in the medicine application field, while the low frequency is used if you keep the NED audio devices in mind. There you have some audio specialists which also rely on higher frequencies, so psychoacoustics, or just the classic field is then distance measurement, like in many cars nowadays, or it's gesture recognition. And that's what I want to step deeper into now. So gesture recognition, where to use it, why. So this picture shows an application within a car. So the multimedia interface, which we would attribute to the consumer field, could also be in the social field like sign language or care robots, just to direct them somehow or interact with them without needing any voice or recognition or app steering. Could also be in health, where the main aspect is the zero skin contact nowadays with the virus spreading all over the world. It's somewhat interesting. And we have, of course, the big industrial field like robot control components or safety, where the interaction, the co-working of robots and humans are helped by gesture recognition or distance measurement. In the consumer field, as I said, we have this car interior, but we have also the mobile devices like smartphones, wearables, and specifically hearables. What are hearables? Hearables are tiny devices like tiny earbuds. I brought several examples here. So they bring audio to your ear, and they are truly wireless in most cases if we speak about hearables. And sometimes they also include a small computer system to maintain fully autonomous operation mode, so not dependent on your smartphone. And even if not, there's a lack of like a display or some human-machine interface, so you somehow want to alter the interaction with your system. And from there, I believe that gesture recognition is a pretty promising way because it's comfortable and easy to use. Just higher the volume by some swiping gesture or lower the voltage, of course. And it's not that important how precisely you move your hand to this device or not. It will get what you want. So you can do it with reduced consciousness. And silence. Silence is like with a double meaning, because if imagine it's not obviously it's not a voice command, and if you have this earbud in your ear and you imagine tapping on the device, just I don't know, double tap to silence or to mute it or to switch it on or off, it will make uncomfortable pressure waves on your ear, so it will limit your device experience. And then it's even more nice to have a gesture recognition, not to suffer from these pressure waves. Right now we see first mobile devices on the market, including gesture recognition technologies. So it's coming to the market. We are there. Of course, the first one I know about is a Google Pixel 4 device, which relies on radar technology. But it's there. And for the hearables specifically, we have an emerging market. And that leads me to my last slide. It's the market of gesture recognition. So from several market analysts, so I wrote the names here, we know that this is a really fast growing market with a compound annual growth rate of more than 20%. So it's heavily growing, and it will reach by the forecasts market volume of $30 billion just by 2025, and just by gesture recognition. So it's not motion sensing or something, it's just gesture recognition, what I talked the last two slides about. And to give you an example, even today, so in 2019, we have a market of 750 million in the automotive gesture recognition market. It's already there. So what will the focus on next developments will be on miniaturization, low cost and reliability. And we believe at the IPMS that a MEMS solution for low frequency is especially well suited for that. So let me sum up, come to the point, close the picture, close the frame. We have unique technology possibilities with an electrostatic drive and the volume utilization combined. We at Fraunhofer IPMS are able to offer an innovative ultrasonic sensor solution, not only for low frequency, but also for higher frequency ultrasonic devices. And for me, it seems apparent that low frequency MEMS are very well suited for airborne ultrasound, which is especially interesting for the gesture recognition market, as it is awaited to get a really multi-billion-dollar market. thank you very much for listening, and I hand over again to Stefan.
Yeah, thank you very much, Bert, for this really interesting introduction in the technology of our NEDMUTs and the application fields behind. During our presentation, there came up a questions I want to share with you. And the question is regarding the application of NEDMUTs in hearables for gestural recognition. Would hair between NEDMUT and hearable block the signal?
No, thank you very much for the question. So, of course, this depends a bit on the hair, but most likely there will be not a very big issue. Depending on the on the density of the hair. What I would expect is that it's not a very good reflecting object, as I want to say, and therefore, it may require extra processing, but it will not inhibit the use. No.
Okay, thank you. Then there is popping up another question. How is a ballpark of the cost for one device?
So the cost of one device, I didn't get the first words, but I still may estimate. Yeah, of course, MEMS do offer in principle the potential to have a pretty low unit costs, but that's highly depend on really high amounts of devices. But as a rule of thumb, you can compare to the maybe MEMS microphone market, which is already there, and there you go with the device costs really below $1 if it's a multi-million device market, which is not that unrealistic for a consumer product. Yeah.
Great. One last question. You showed the technical, the NED transducer approach, and you showed us the transducer inclusive the 5 transmitter and 4 receivers. And about what sizes are we talking about with this NED actuator approach?
Yeah, okay. Thank you very much for this question. The device, the whole demo chip device is like 10 by 10 millimeters. So from the surface area with a thickness of around 1 millimeter from the 3 wafer stack. And the actuators themselves, they are pretty tiny. So they have a length of below 1 millimeter and a thickness of several 10 micrometers. So that's a bit depending, that's application specific, that's also frequency specific, but it's like a human hair, a short human hair if you want. Yeah, really densely packed into this chip area.
Great, thank you very much. There came up another question afterwards. What is the typical acoustic bandwidth of these devices? It's from Hamilton.
Again, this depends on the design. So with this demo chip, we wanted to prove the feasibility of this concept for ultrasound range for low frequency ultrasound devices. And I guess with our approach, this lithography on the surface and then extruded to the volume, we are able to address different needs. Right now, that's all I can say.
Great. Okay, thank you very much, Bert. This seems to be the last question at the moment. If there are popping up more questions afterwards, please feel free to contact Bert or me, Stefan Tietze. And yeah, I hope you enjoyed our webinar and you got a detailed view about our NED research topic in the area of low frequency ultrasound, and hope we see you soon for the next webinars. Have a nice day and bye-bye.
Thank you. Bye.